Welcome to this final video on the forces and space scheme. This one is about circular motion that's caused by non-contact forces, and the main non-contact force we'll focus on is gravity. And I like to start this lesson with a bit of a thought experiment. I think this was, I think it was Newton that came up with this, but anyway, that doesn't matter too much. But the idea of the thought experiment is that we've got a cannon on the top of Mount Everest. So here's Earth. And we can start by imagining the cannonball is fired with a certain velocity and it goes this far, it gets to point A. Next time the cannonball is fired with a slightly greater velocity and it gets to point B. It goes a bit further. Now we can imagine that if you fired the cannonball fast enough, well then it wouldn't ever actually land. It would just keep going round and it would always be falling, but it would just never actually make it back to the surface of the Earth. If you just kept firing it faster and faster and faster and faster, there must be some velocity at which it just carries on round in a circle. And this is really, really interesting. It wouldn't work, incidentally, on the real Earth because of air resistance. But I think this is, again, another illustration of Newton's genius, was that even at a time when most people thought a vacuum, the very idea of vacuum was impossible, he said, well, what about if this were to happen in a vacuum? And what he did was apply the same ideas, let's call that trajectory C up here. He applied the same ideas that we've been applying to work out what was going on. So if we zoom in on this bit here, sketch that on this part of the page over here, what I might draw for students here. So if this is Everest and this is my cannon, like that. So we can sketch trajectory A, for some reason that's a difficult word to say, like this. And what you want students to do is think, okay, this is my cannonball, in what direction are the forces acting? And again, we're just coming back to the same ideas again and again and again. We're unpicking that Aristotelian idea that there's going to be some sort of force in the direction of motion. What we want them to recognise is the only force that's acting is the weight acting downwards like this. And therefore it's going to accelerate downwards. Let's think about trajectory B. Well, it's kind of the same thing, isn't it? If the cannonball is over here and we ignore the effect of air resistance as Newton did, well then just going to be the weight acting downwards again, and therefore in both cases they're accelerating downwards. And I think students should find that relatively simple to get their head around. But what's interesting then is if we think about C. Now in I can't say that word. Trajectory C, which I'm going to draw here, let's draw the cannonball again. Drawing it up here because, as we've seen here, it never actually gets any closer to the Earth. It keeps falling, and yet it just never gets closer to the Earth. And in what direction are the forces acting? Well, it's no different to A and to B. The only force acting on this is straight down towards the centre of the Earth, like this. It's just the weight. So what we can do here is then map this onto our broader diagram, our bigger picture. This is building on what students already know. So let's draw the cannonball, I don't know, let's say over here. Imagining this cannonball could make it all the way around and the air resistance wasn't anything to worry about. Well, in what direction would the force be acting? This is downwards, but really it's down to the centre of the Earth. So in this case, if we were to draw it here, we'd be drawing something like this. This is the weight, again, acting towards the centre of the Earth. Now hopefully at this point students should think, this looks familiar. This is what we looked at last lesson when we were swinging things around on pieces of string. And what this thought experiment illustrates, well, lots and lots of different things, but one thing it illustrates is that actually this cannonball, as it moves along in this seemingly straight path, is constantly accelerating downwards towards the centre of the Earth. Now, this is kind of confusing when you look at it on a small scale, and this is a very small piece of the Earth. That's been made to look flat, but when you look at it on a big scale, we see that actually it's just the same type of example as we saw before. It's moving that way, it's accelerating towards the centre of the circle. And this is what I would want students to recognise, that it's exactly the same as those examples we saw previously. So it's constantly accelerating. It's not because it's changing speed, it's travelling at a constant speed, but it's constantly changing direction. Now, the other surprising thing about this is that let's think about someone like Tim Peake, who was in the International Space Station. So the final thing that I'm going to do here is sketch a satellite out in orbit. And I'm going to exaggerate the scale a little bit here. So I'm going to draw the Earth. In fact, I'm going to draw the circular orbit first, and then I'm going to draw the Earth in the middle. So this is not to scale. But a big misconception students have here, and again, my scale doesn't help with this, but anyway, this is just to make it a bit simpler to look at. But a big misconception students have is that they think, okay, if Tim Peake is on a satellite out in space, so we can draw the kind of two little wings like that. This is the satellite, so it's travelling. We can make it go in the other direction if you like. Let's go this way, just to keep things interesting. It's travelling like that. When they see Tim Peake in the International Space Station, and they see that he's kind of weightless, we use this word which is super misleading. They think that's because there's no gravity acting upon the satellite. But we know now, if there was no gravity acting, well, this thing would just carry on in that direction. There must be something that's keeping the satellite going round and round and round and round. And that something is, as we've just said, this gravitational attraction. So I'm going to draw my force in towards the centre of the circle, like that. And I'll just put gravity for now. Really, it should be the gravitational attraction. So that's the only force that's acting on this satellite. And therefore, this thing must be accelerating towards the centre of the circle. Now, the reason for doing this whole thought experiment first, rather than just telling students, is because what we want students to recognise is circular motion because of gravity is exactly the same as what we saw in A and B. It's free fall. The only difference here is because it's travelling fast enough that it never actually loses height and falls to the ground. It just keeps going at the same height above the Earth. And this is a really important point about circular motion, is that if you're going fast enough, you can keep going in a circle, even if the circle becomes quite small. But the smaller the circle, the closer you are to the centre of the circle, the faster you have to keep going. Now, that's the last thing that we want to talk about in this scheme of work. So right at the beginning of this, I think in the very first lesson, we stated that Earth has a year which is 365 days long. Mercury years are a lot shorter, I think about 4 times shorter. And we said that was because Mercury has a much smaller radius, it's much closer to the Sun, and therefore it has less distance to travel. What we can do now is give students an even more sophisticated account, which is, well, that's kind of true. It does have shorter distance to travel, so if they were travelling at the same speed, well, it wouldn't take as long to get round. But there's another reason as well, and that's because Mercury is close to the Sun. It's got to go faster and faster and faster around the Sun, or not faster, it goes at a constant speed. It's got to go faster than Earth around the Sun in order that it doesn't crash into the Sun. And so, it's travelling a shorter distance, it's also travelling faster, and that's why the time that it takes to complete its orbit is much lower. So, that rounds off the scheme of work nicely. Oh, and I didn't talk about Tim Peake, sorry. Last thing to say is about Tim Peake. So we think he's weightless, but actually he's just in free fall. So he's a bit like someone falling through the sky and they couldn't move up or down because they're falling. And that's a really mind-blowing thing for students to try and get their heads around. And I think while that's difficult and challenging, the fact that we can really unpick the way students think about these things that they're all familiar with from movies and TV and so on, and really give them a brand new way of thinking about it that profoundly reorientates their relationship with the world, that's what makes science teaching super inspiring. And I hope you have some really rich, kind of wonderful, and I use that word wonder deliberately, wonderful conversations with your students in which they're really inspired to go on and find out a bit more about these just extraordinary ideas. Anyway, I hope these videos have been useful. Thank you very much for watching.